Hello, this video will take you through an example of how to solve a trig equation that contains a double angle. Now, a similar procedure can be used if you're solving a trig equation that contains a triple angle or a quadruple angle, or really any multiplier on that angle. But for our example here, we'll use a double angle. So we see that the ratio that's involved is sine 2x and not just sine x. So there is going to be kind of one additional step that we include in our solution in order to solve equations of this form. So similar to the last example, the same thing we're going to start with is rearranging so that the ratio is isolated. So in this situation, that means we're going to divide both sides of this equation by 2. So by doing that, we get sine of 2x is equal to negative a half. Now, if this was just sine of x equals negative a half, then we know to proceed by looking for in which quadrants do we have solutions to this equation, and considering that the sine ratio is a negative value, and using either our special triangles or our calculator to solve for beta. And we're going to proceed in a very similar way. So in fact, we're kind of almost pretending for a second here that we just have sine of x in this equation. And so if we consider that, then we look at our Cartesian plane, and we know the sine ratio is negative in quadrants 3 and 4. So we're going to have some solutions in quadrant 3 and 4 here. Again, just considering this 2x as a single angle for the moment. So if we do that, then our first solution is going to be this angle here, so that's theta 1. And our second solution goes all the way around to quadrant 4, and we'll call that theta 2. And both of those angles would have the same related acute, and we know that we can write out the related acute ratio as sine beta equals the positive value, so just positive a half. Now, the sine ratio that's equal to a half comes from our special triangles. So if we draw out the special triangle that would give us that ratio of a half, we have pi over 6 and pi over 3. And this side is root 3, this side is 1, and this side is 2. And so we can see here that the opposite over hypotenuse that gives us 1 over 2 would be for the reference angle of pi over 6. So that gives us that beta is equal to pi over 6. Okay. So looking at our diagram, that would give us that theta 1 is equal to pi plus pi over 6. Actually, hold on. I'm going to go back for a moment because we don't actually have thetas here. We have x's. So let's change these to x1 and x2. You want to make sure that you're keeping your variable consistent with what was given in the question. So this is x1, and we'll change this one to x2. There we go. So when we solve for x1, that would be pi plus beta, so pi plus pi over 6. And that would give us 7 pi over 6. Right, 6 pi over 6 for pi, plus another pi over 6 gives us 7 pi over 6. So x1 would be 7 pi over 6. However, we did not have just an x as our angle here. We had a 2x. So let's make one slight adjustment to this. Instead of x1, this is going to be 2x1. And so when we solve for that, this is 2 times x1. So if we rearrange that for x1, divide both sides by 2, we get that x1 is actually 7 pi over 12. So that's the difference when we're solving for solving a trig equation that involves a double angle. Or that's one of the differences anyway. Okay, so we've got x1, or one of the solutions to this equation, is 7 pi over 12. We're going to do the same thing with the second angle. So I'll start with the 2x2 on the diagram here this time. So 2 times x2 is 2 pi subtract beta. So 2 pi minus pi over 6. and 2 pi minus pi over 6. So 2 pi would be the equivalent of 12 pi over 6. So 12 pi over 6 minus 1 pi over 6 gives us 11 pi over 6. And dividing both sides by 2 gives us that x2 is equal to 11 pi over 12. So that gives us two possible solutions to this equation, but we're actually not quite done yet. So let's rewrite that equation. We had, the original equation was 2 sine 2x is equal to -1, and we had simplified that to sine of 2x equals -1/2. And so far we have two solutions. We have the solution x1 is equal to 7 pi over 12, and x2 is equal to 11 pi over 12. However, these are actually not the only solutions between 0 and 2 pi for this equation. So next we consider the graph of the function y equals sine 2x. So the graph of y equals sine 2x would be similar to the graph of y equals sine x, except that instead of a period of 2 pi, this graph will now have a period of pi. Or in other words, the graph has been horizontally compressed by a factor of 1/2 from y equals sine x. And so starting at the origin, this graph would complete 2 full cycles before getting to 2 pi. So halfway between 0 and 2 pi would be pi. This would be pi over 2. This would be 3 pi over 2. So we had that sine of 2x is equal to -1/2. Well, if I show -1/2 as a y value on this graph, it's approximately here. So this is the line y equals -1/2. And this graph is y equals sine of 2x. So I can see on this graph now that the first two solutions we found where these two graphs intersect, so where y equals -1/2 intersects with y equals sine 2x, the first point where they intersect is here, and that's the first solution that we found, 7 pi over 12. Okay, so that's x1. Here's the second point of intersection, and that's a little bit less than pi, so it makes sense that that's our x2 value, which is 11 pi over 12, just a little bit less than pi. And we actually have two more solutions that are happening before we get to the end of our given domain. Remember, we're solving this equation for x values from 0 to 2 pi. So we want to make sure that we list those answers as well, because those are also solutions between 0 and 2 pi. So to get those other two solutions, we recognize, first of all, let's label this one as x3, and let's label this one as x4. So we recognize that between x1 and x3 is one period of this function that we've graphed. And one period for y equals sine 2x is equal to pi. So if we add pi to x1, that should give us the value of x3. So we have x3 is equal to x1 plus one period, which in this case is pi. And so x3 will be equal to 7 pi over 12 plus pi. And I can get a common denominator here, so pi can also be written as 12 pi over 12. And so x3 is equivalent to 19 pi over 12. So that gives us our third solution. And to get our fourth solution, x4, again, we recognize that between x2 and x4, that's a difference of one full period. And so again, if we take the solution that we had for x2 and add the period of pi, that will give us x4. So x4 will be 11 pi over 12 plus pi, which can also be written as 12 pi over 12. And that gives us that x4 is equal to 23 pi over 12, which is in fact just a little bit less than 2 pi, and that makes sense based on the graph that we've drawn here. So when solving trig equations that contain double angles or triple angles or any other kind of multiplier on the angle, we find our first two solutions by using the Cartesian plane and by labeling that diagram for the Cartesian plane with double angles or triple angles or half angles, if that's the case, and solving those respective for those respective answers for the first two solutions. And then for any remaining solutions, in this case, there was two more solutions between 0 and 2 pi. For a triple angle, you might have 4 additional solutions for a total of 6 solutions between 0 and 2 pi. And for a half angle, if this was sine of a half x, then you may only have one solution between 0 and 2 pi that you end up solving for. So to see if there are any additional solutions, it's always a good idea to draw out the function related to the equation that you're trying to solve.